Okay, hello everyone, and welcome to the fourth session of our air conditioning and ventilation webinar series. My name is Babak. I would like to welcome you to this session. Um, as always, we've prepared some very nice simulations along with some analysis of the results for you. I hope we can go over all of them, have enough nice discussions, and of course at the end there's going to be questions. But before I start and move to the content of the webinar, I would like at least a few of you to raise your hands so I make sure everybody can hear me. Okay, great. Thank you. So I have a few people. Thanks a lot. Then I hope everybody else also hears me. And we don't have any other technical problems difficulties that stops us from continuing. Okay, so as I said, this is the fourth session of our air conditioning and ventilation webinar series. We already covered different topics. We tried to address several problems that might occur on a regular basis in the applications that are close to this theme. And here in this session, we're going to talk about clean rooms. But before that, a very quick introduction of myself. So my name is Babak. I am the senior fluid dynamics engineer here at SimScale. My background is in both computational and mechanical engineering. I have experience in different types of flow. Just a few examples, both compressible and incompressible flow, heat transfer at the same time, mesh-free methods on top of the normal finite difference, finite volume types of modeling. At the same time, I have some experience in technical computing, high-performance computing, and kind of these areas that are closely related to the modern CFD, both in terms of theoretical knowledge and also knowledge to actually perform the simulations. So today I'm going to talk about, this is the agenda for today. So as I mentioned, the application that we focus on is contamination of in a clean room. So we will get to details of it, what is a clean room, what kind of contamination we're talking about, and what is the significance of this kind of analysis. Before that, I will have a short introduction about CFD and SimScale in particular, the kind of product that we offer. I will keep it very short, and then I'll move on to some more specifics about the clean room and the application of CFD in this area. As I said, we've prepared a number of simulations for this theme. So what I will do is to first show you the kind of geometries that we're going to work with, go through the specifics of the simulation. Once we know what kind of physical problem we're going to tackle, then we will have a live demo on the platform. After that, I will come back to these slides. We will have a look at the results. Like the previous times, we try to run some sort of analysis on them to have an understanding how simple changes, really simple changes in the setup of the problem could result in really meaningful changes in the outcome of the simulation. How these kind of scenarios, how this workflow could help with our decision making in terms of developing a new product. We also have an assignment that I will show to you. We've also made it available already for everybody who's interested. And at the end, we have a Q&A. So mark down your questions, and I'll try to address as many of them as I can at the end of the session. So with this, I think for those of you who are not familiar with SimScale, we started at 2010, but the development of the platform started at 2011. So 1 year after the company started initially as a consultancy. But now we have a much larger team. We have customers and users from over 190 countries around the world. We're active in different parts of the industry, and every week we have new users, new kind of capabilities that are added to the platform. So it's really a very live and changing environment. A quick reminder why we have this much focus on running different simulations and in the end trying to analyze the results. So this is how we have the traditional design process. We start from a design, we have physical prototypes, we have testing, and based on the results of the test we might make some modifications to the design. We have to repeat these 3 steps over and over until the kind of requirements that we have are satisfied, and then we move to manufacturing. And in the modern day, actually today, we have changed this traditional design process using the simulation. So those 3 steps in the middle are now replaced by actually 2 steps in the middle, and specifically simulation is replacing 2 of the steps which were physical prototyping and testing. The advantages are countless. It's much easier to do. It's way cheaper. It's feasible for everybody to actually perform simulations compared to the requirements that that physical prototyping and testing has. So overall, it really introduces a new way of designing and developing a new product. What we offer, our platform offers here, is accessibility of these features, of these simulations features for everyone. So you don't need to have any sort of special hardware or software. You don't need to have access to any sort of computing power, or even you don't need to have the knowledge to set them up, deal with the costs, nothing. It's just all provided. It's very cost efficient compared to other solutions that are available out there. It is the costs are very low. For public use, it's completely free. You have access to all the features, and of course, we offer additional features on demand and for special jobs. And at the same time, it's available for everyone. It's both in terms of availability, accessibility, as I mentioned in the first bullet point here, and at the same time in terms of the content. We have aimed for this platform to be usable by everyone, and as you go forward, you will acquire more and more knowledge to really become someone who could use the simulations in a meaningful way. To support this, we have about 15,000 projects in our community, and this number is actually growing every day. And as I mentioned, we have different areas, different types of physics that we allow in our platform. So for fluid mechanics, we have both incompressible and compressible simulations. We have heat transfer, multi-phase, and all of them, of course, with or without using turbulent models. We also add some advanced concepts on top of each of these analysis types, like using of rotating zones, for example, in applications like rotating machines, using porous media, also very widely used in applications of aerodynamics, several applications actually. We have free body motion, where you do not want to fix a part of your domain, but you want to see how the flow affects its motion. And we also have particles, where you want to inject particles that affect the flow, and in return their motion is affected by the flow. So these are all available and publicly, for free, available for the users on our platform. So with this, let's now get to the topic of today's webinar. As I mentioned, this is about ventilation in clean room. Let's see what a clean room is. If you're not familiar with this, I will quickly go over a couple of applications where such a setup is is used nowadays, and then we go to set up our simulation. So clean rooms are environments that have to be very carefully monitored. So to be very accurate, a clean room is defined by an environment where the contamination is controlled. There are several types of clean rooms, several designs based on the kind of application and industry that they are being used in. So we have clean rooms in medical applications, pharmaceutical, biomedical, aerospace, manufacturing of electronics, nanotechnology. So really in a very broad range of applications, clean rooms are very common. So the idea is that for development of, for manufacturing of any of these products, the level of contamination in that room, in the air that is flowing in that room, must be controlled. So there are different standards, but essentially all of them each standard is defined by a certain number of particles which have a certain range for their size in a, let's say, 1 cubic meter of air, or in a certain volume of air. So depending on the application, these numbers change. They could become very strict, and that's why this is why the contamination control in a clean room is quite important. And with that, of course, comes the ventilation. The idea behind having a ventilation is to effectively control the contamination if there is a leak. If, for example, there is a door, there is, I don't know, a window, anything like that, or the connecting rooms that could cause the levels of contamination to go up. So we need to have an effective ventilation. At the same time, it's a matter of safety. It's not always about manufacturing. For example, in medical applications, we could have rooms that are designed for patients that have contagious disease. So the idea there is to completely contain the certain microorganisms that are responsible for spreading of this disease, completely contain them in this room. So here it's really a matter of safety. And of course, on top of both of these, the design needs to be cost efficient. So it has to, at the same time, that fulfills requirements in terms of safety and contamination levels. It also must be reasonably priced. So how CFD can help here? So as I mentioned, we could easily design a ventilation system in a simulation. There's no manufacturing at this level involved. You just have your, for example, CAD model. You design certain features that appear to be either required or helpful, and you run your simulations with it. Once you have that, you can have a very comprehensive map of your results to see levels of contamination, the flow field, any certain characteristics that you might be interested in are very easily could be monitored in after your simulation is done. You could compare the results of several types of simulations, both real-time and in the steady state behavior, and in the end, due to certain regulations or certain features that are required, you could have these quick what-if scenarios where you want to add a feature to your simulation, and without having to do too much work, simply launch the workflow from the beginning and see what comes out from the end. So this is how CFD could contribute to this contamination control and ventilation application in Cleanroom. So so let's have a look at the case that we are going to talk about. So we have 3 designs that I will show in the next slide, what those designs are. But let's see what kind of variations are available. So the first one is the layout of the inlet duct. So let's say from the ceiling. It could be from the ceiling or anywhere else. In our case, we've placed it on the ceiling. We could have a central or distributed layout, meaning the air could enter from exactly or roughly one inlet into the room, or from several ones that are kind of distributed across the room. So this is one variation. Same concept. The outlet could also be have two variations. Either it could be along the floor, or we could have a raised floor setup. A raised floor is a setup where actually the outlets are placed on the floor of the room through tiles that actually act as an outlet, and then we could have actually this all over the floor of the room, and that acts as an outlet, as opposed to having certain outlets on the walls at the bottom of the walls where take the air out of the room. We've also added some a source of contamination. We call it contamination leak here, to see in case of a leak what happens to the contamination level. We use use passive scalars as to represent the contaminant. The reason is that the size of the particles that normally are interesting in these applications are quite small. Considering that and the kind of velocity profiles that are typical of these applications, there's really very minimum, if any, effect of particles on the flow. And these particles are so small that they essentially follow the patterns of the flow. That's why we use passive scalars. We have kept the inlet flow rate, mass flow rate constant for all of the designs to kind of give them a fair comparison in the end when we are looking at the results. For the case of these designs, we consider a laminar flow condition, which is completely realistic, but there are also turbulent variations where the inlet is intentionally turbulent. But as I said, in this webinar, we focus on laminar cases. So here is our first design. This is the base design that we have. We have a central inlet. You see we have 3 inlets, quite dominant on the ceiling of the room. We have several outlets that are placed at the bottom of the wall along the floor. We call this a single pass. Actually, all 3 of the design are single pass. But to just explain the terminology, single pass means there are a number of inlets and a number of outlets, but the air that leaves the room leaves the room. It does not get recirculated back into the room, and this is what single pass means. So this is our first design. Our second design is called, so we have distributed inlets. So as you see, we have now we have 9 inlets on the ceiling. They're distributed, so they aim to give a more or less uniform flow of the air from the ceiling. But we also call this this is also very typical of negative pressure clean rooms. So negative pressure clean room is a design that is particularly suitable for safety. The example that I gave earlier in controlling the contagious disease, negative pressure clean rooms are actually very useful in those areas. This is how this is a design where we keep the pressure of the room slightly below the pressure of its surroundings, so the rooms that could connect to it. So in case there is a connection between these two, maybe a vent is open, a door is open or something, the air is only allowed to enter from outside to the room, so from the places that have high pressure to the places that have lower pressure. The idea is again to not let any of the air inside the room to leave, and this is why it's called a negative pressure clean room. So this was the second design. Again, distributed inlets at the top, but the same same distribution and outlet of layout of outlets at the bottom. And our third design is a little more advanced. We call it raised floor. As you see, the floor is slightly raised. It's tiled with these certain type of tiles. You can see we've shown a one of them here that has certain these patterns inside it to let the flow let the air flow through it. So these are completely covering the raised floor, so the air is allowed to go through them, and then we have large outlets at the under the floor to actually let the air out. So this is the third design. It's called raised floor, and we keep the inlets the same as the second case. So we gradually, as you see, try to explore different aspects of the design. And as I said, we've included in all three cases a contamination source to see what happens if, in case of an emergency or if something goes wrong, what happens with the levels of contaminant in the room. Okay, so this was the physical case that we are going to tackle. Now let's have a look at some workflow and then some specifics of the simulation. So the workflow is similar to what we normally have. So we have 3 steps. We start with a CAD upload. After that, we mesh and simulate. So we first create a mesh, which is discrete representation of our domain, and then we start to perform a simulation. Once we have these, we have the results. It's time to put them in the post-processor, maybe generate the kind of data that we need, and based on those make design decisions. In this case that we're going to demonstrate, we're going to see which one of the 3 designs satisfy our requirements better. So for the first part, the part that we upload a CAD model, we have an integration with the Onshape platform. So it's easy to, as you can see here, you can, instead of uploading a CAD or a mesh from your own machine, what you can do is you can directly import from Onshape. When you click this, as you can see here, a window opens and lists all of your CAD models that you have on Onshape. You can choose which parts you want to import and simply click import. It will directly be imported here. Of course, for that you need to have an account on Onshape. Regarding the simulation, these are some generics about the simulation that I'm going to show to you later. So we started with a hex dominant parametric mesh generation. So this is there are several parameters. I will show the most important ones, and that will be it for the meshing. In terms of the simulation, as I said, we used passive scalar transport due to the conditions of our flow and the size of the particles that are involved. So the contaminant is represented by a passive scalar in the air. The Schmidt number is 0.7. Schmidt number is the ratio between the diffusion due to viscosity and the diffusion due to, let's call it the mass diffusion due to molecular diffusion. And the diffusion coefficient is set to 2 to the minus 5, 2 to 10 to minus 5, which kind of is a property of air. We run 3 cases, all of them steady state, because in this case we are more interested in seeing the contamination levels and the flow conditions on this in this steady state in our domain. As I mentioned, we are working with laminar flow, so the turbulence modeling is just laminar. The inlet velocity is at the inlet, and top is 0.05 meters per second, and for the contaminant that comes from that source, it's 0.1. And one more thing, as I said, in all three of the cases, regardless of the type of the inlet they have, we have the same overall mass flow in all of the three cases. The kind of output that you're going to look at later are flow patterns in 3D and pressure distribution in the domain. This would be one. We also have a look at the scalar distribution. So this will be tied to a number, to a scalar number that in our case ranges from 0 to 1, and this is a kind of a representation of a certain number of particles in a volume of the air, which is, you know, the way the standard of a clean room is measured. We also look at the time average, steady state time average results, which are the distribution of the contaminant in the domain, and also average flow rates and scalar value at the outlets. Okay, so with all of this, I think we're prepared now to switch to the platform. I've the project here open. Let me just drag it here. So as you see, we have the AC ventilation session 4 clean room project. So here I have it in my project overview page. I will show you these couple of geometries. Let me just first open the project, and from there I'll take it, you know, step by step to show you how the simulation is designed. Okay, so first let's start with having a look at the geometry. To start, I will just hide these two faces so we can have a look inside the room. So this setup belongs to the first design. These three parts that I'm going to select now are the inlets. As you can see, we have, simply for the sake of demonstration, we have a couple of features inside the room, and here, this one that I'm going to highlight now is our source of contamination. Rest of our designs are kind of similar. Maybe let's have a look at the third one as well, because it has both the distributed inlet and also the tiles at the floor. Okay, so let's just again hide these faces on the top. Okay, so you will see these nine inlets. Maybe highlight them here. You can see it's a distributed distributed inlet, and also we have the tiles. So you see, I think you should be able to see them with different colors at the bottom. Maybe again I'll just highlight them, a few of them. So these are the tiles that are placed on the raised floor. So for the meshing, we have, from each of these models, we have produced a mesh. Let me just show you how it's set up, and then I'll show you one of the meshes itself. So the most important parameters that are you know, useful to have some knowledge of are these ones. So here we have a general representation of the size of the mesh. It's not the final size of the mesh, it's how we initially create our mesh and work our way by refining the mesh. So normally we automatically create these numbers, so unless you know you want to use larger numbers, you don't need to really change these. Here's also the number of the computing cores. This also is set based on an estimation of the final number of the cells in our mesh. What is interesting to have a look at are mesh refinements here. So as you see, we have 5 different refinements. Let me show these ones first. So this one, if I assign it, you will see it's assigned to the whole geometry. So what it does is that it adds two levels of refinement to the surfaces that belong to this solid. So essentially what we do is that we create a base mesh, and then for every surface that belongs to the main body of our geometry, we add two levels of refinement. This creates smaller cells, which means it's going to be easier to generate an accurate result, get converged results. Same here. So let me just switch to another one. We have another surface refinement. This time it is one level higher, so it has three. Let me show you where you can find these refinements. Again, I will hide these faces, and then I select the assignment. So you will see these three parts inside the domain. They all have three levels of refinement. The rest is kind of the same. We have a feature refinement, which means it automatically goes through our geometry, and whenever there's a feature like a corner, an edge, anything that requires a higher number of cells to resolve, that feature accurately, it adds a certain number of levels based on the distance from the feature itself. We also have a region refinement. This region refinement means that we create, in this case, a Cartesian box. So you could see it with this light blue color. And what we will do is to add a certain number of refinements to all of the cells that are inside this region. So in this case, all of the cells that are inside this rectangular box get refined to to level 2. So I think this should give an idea how the meshing is set up. I'll just click on one of them to show you what the mesh looks like. So here is the mesh. Here are the three inlets. In here we have the outlets, so 3 on this side and 3 on the other side. If you want to have a look inside out as well, I will maybe just hide all of this, and then you can see. So as you see, with the kind of setup that I just mentioned to you, everything is resolved very, very nicely. These parts that the features are more are smaller, require more cells. You see the size of the mesh is also smaller. So this really is a good mesh. You could completely feel safe to move forward and set up our simulation after the setup. The other two meshes, the setup is also very similar, so I will not spend time there. But after the webinar, just feel free to go through these, also our step-by-step tutorial, to see how creating such a mesh works. Okay, now let's move to our simulation designer. We have prepared our mesh. We want to have a look at one of the cases. So I will go through details of the first case and then very briefly show the setup for the other two cases, so you see they are very similar. So the choice of analysis type is fluid dynamics passive scalar transport. We have only one species on top of the air, so I will choose one here. The turbulence model is laminar. We are interested in steady state, so when you choose it, automatically a simple solver is selected for you. So this is the right setup. After we save this, we can move on. First, we select the domain. This is the first design, so I'll select the corresponding mesh, and that's it. If you're interested, you can see, have a look at the details of the mesh. In this case, we see this mesh has something like 1.4 million volumes. Okay, so once we have that, we can move to actually, put the physical parameters inside the simulation. So the first two, as I mentioned, are the turbulence Schmidt number and the diffusion coefficient. So as I said, we take 0.7 for the turbulence Schmidt number. Also, this diffusion coefficient belongs to, corresponds to how much diffusion, how much molecular diffusion takes place when we have these passive tracers inside air. Now also have to add a material, so you can simply right-click here and add a fluid material. This is already done. You can also maybe click on the material library and you will see a list of materials. Select the one that you actually want to choose, click Save, and it is automatically added here. This is assigned to this region 0, which is the main domain, our main computational domain, and the only property that is needed, which is automatically provided by the library, is the kinematic viscosity. Then we have initial conditions. These conditions specify how at the beginning of the simulation, when still no computation has taken place, how the fields look like. So in particular, we have to define what the pressure is, we have to define what the velocity is, and we have to define what the distribution of the passive scalar is. As you see, in all of these cases, we didn't have to do any special treatment. It was just 0 for velocity, 0 for pressure, and also 0 for passive scalar. So I think the other two are understandable. About the passive scalar, as I said, what we will do is to say we have a range of 0 to 1 that correspond to a distribution of passive scalar, which means that the number 0 means there is no particles in, let's say, 1 cubic meter of air, and number 1 means that there is an assumed number of particles. So this is how we do this simulation. Later, once we have the distribution of passive scalar from 0 to 1 in our domain, we could simply map it to the number of particles that we are interested in. So with this, we have to set up the boundary conditions. We have 4 boundary conditions here. First, the inlets of the air. We have all those, all the 3 inlets. Let me show them. Yeah, they're assigned here. The 3 inlets, we choose a normal velocity inlet condition. We just have to specify the right value of the velocity, which is in the z direction, and that's it. Since the air that comes inside the room, we assume it has no contamination. We put 0 for passive scalar. Of course, if this is not the case, this number could be adjusted to represent that case. We have another inlet. This belongs to this contamination source. So as I said, we have a contamination source. We assume the velocity of 0.2 meters per second, coming out of the source, and there, because we are representing some concentration of passive scalars, we put 1 here at that outlet. As you will see, this is going to be, when we look at the results, the source of the contamination entering the domain. We have outlets. So in this case, we used a custom boundary condition, which is very similar. I mean, the idea behind this is very similar to pressure outlet. The only difference is we wanted to set inlet outlet for passive scalar. So inlet outlet is a combination of fixed condition and 0 gradient. So it says that if the flow in this outlet boundary that I've assigned it to, if the flow is normally moving out, it's normal. It's the same as 0 gradient, which is the same as pressure outlet. But if the flow is reversed and wants to enter the room, we use a fixed condition, and that number is this inlet value here, which means 0. So if the air leaves the room, it's a normal pressure outlet condition. If it enters, we assume no contamination is entering. Again, this assumption could be adjusted. It's not really, it's very easy to change it. It's not, the result of the simulation could may be sensitive to it, but it's just very easy to change and see. And then we have the walls. Again, the rest of the domain, so not the inlets and the outlets, are going to be walls. We assign a zero gradient for pressure and passive scalar, and a fixed value of 0, which represents the no-slip condition for walls. So that's it for the boundary conditions. Also very similar for the other two cases. The only difference would be that they're assigned to different entities of our mesh. That's it. We don't need to set any sort of advanced concept, so I will jump over this. The numerics also, we changed them slightly to use a little bit of relaxation for pressure and velocity, and also we used the multi-grid solver for pressure. Since this is a little outside the scope of what we're discussing here, I will not go through more details. But of course, I'm open to discuss this in the community if anybody in the forum, if anybody is interested. So the simulation control, the same. We assume we want to simulate it for about so in the steady state, but longest for 3,000 seconds, and we use 16 cores to run this. This is kind of an estimation based on how many volumes we have in our mesh and how long we want to run our simulation. I put a maximum runtime of 30,000 seconds to just make sure my simulation does not run longer than that, and that should be it. So here is the run. You see it ran. It took about 114 minutes, a little less than 2 hours. You can see the convergence plots very nicely converged here. Of course, we could always play around with this to make them look slightly different or change the convergence behavior. But for the sake of our work in this webinar, these are completely reasonable. The same applies to the other two. As you see, we have roughly the same. We have the same boundary conditions. They're simply assigned to different entities that correspond to the mesh that we assigned them to. And so here is the run for the second case. It took less time to converge. And let's actually have a look at the third one to see what happened there. So this one is a more complex case. We have the tiles. I think also the mesh probably is going to have much more volume. So here's 4.9 compared to I think 1.4 we had in the first case. So this case takes longer, about twice as much as the first case to converge. Okay, so so these were the simulations. Again, as I said, they're very similar, so we don't need to go through the details of all three of them, but this should give you an idea how the case is set up. Now let's move back to the slides and have a look at the results. Okay, so in this slide we have a look at the flow velocity on Y section. So we created 3 sections under at the same places for, of course, all of the cases to see how the flow velocity looks like. So let's start with the design on the left. So the first design. So as you can see, we try to point them out here by these red circles. You see a number of recirculation zones. So recirculation zone is essentially where the flow, where actually the contaminant is trapped. We could kind of treat it like that. So if you have a recirculation zone, when a number of particles, when a certain population of particles enters that recirculation zone, it takes a long time for them to leave the recirculation zone and, for example, go to other parts of the room or go through the outlet and leave the room. That's why it's very important not to have these recirculation zones. Otherwise, the contamination gets localized at part of the room, and through diffusion, slowly, gradually, again entering the rest of the domain. But it never successfully and efficiently leaves the interior of the clean room. So you see again the same, somehow reduced, kind of in a meaningful way also. Recirculation zones, smaller ones, also it's fewer in the case 2, but we still have a few of them in the domain. For the third case, which we went through more trouble, if you remember, the simulation took longer, the design was more complex. We have firstly smaller recirculation zones. Also, they're not as structured as what we had in the other two cases. If you look at them, we just really pointed out to one of them here, which seems quite established like the other two, but the rest of them have a different form, different shape than the other two. So here maybe a little qualitative, but we already see some improvement when we look at these results in the case 3 compared to cases 1 and 2. Now sorry for that, let's go to our next slide. In this case, we again look at the flow velocity, but in an X section. This time, this section is placed in the middle of the domain. Or I think, yeah, both of them I think are, yeah, all three of the cases we have the flow velocity and the X section in the middle of the room. So again, from the design 1, we see a number of recirculation zones, particularly one of them that is very well established, and you can see them how prominent they are these two under these kind of a table. So you see they're very well established. It means that it's very easy for some contamination to get trapped there and stay there for a long time. So this is not desired. Looking at the second design, we somehow see the same patterns. So both the recirculation zones that exist on other parts of the domain, also those two that are placed under the table, we see they somehow are the same. It's interesting to see that except for the ones that are placed under the table, the size of the recirculation zones in this plane are somehow smaller than the ones we had in the previous results. If we look at the third design, here we see almost no recirculation. So here the results obviously look different. They obviously have a different quality compared to the first two cases. Specifically, if you look at the flow pattern under the table, there's no recirculation. So it means that even in those two, let's say, remote parts of the domain where it's very likely for contamination to get trapped, we have a nice way of removing the contamination from the domain. So here we already see how the extra mile that we had to go to design this third case pays off. Okay, and one more section, but this time a velocity profile, but this time on a different plane. So again, an X section, but we put it on the side. This is the plane that is placed in the middle of the contamination source, the inlet, of the contamination source. So this is interesting because it somehow shows when the contamination, when the particles enter the room from this contamination source, the flow velocity, the flow pattern on this plane is very influential on how they're going to be distributed. So let's have a look at these three snapshots closely, because in a later slide we will see how these flow patterns really affected the distribution of the contamination. So in the first one, we see really many recirculation zones on this plane. So what it implies is that we have first a number of large zones that the flow is recirculating, and second, these are low velocity regions, which means that when a particle enters this, again, it takes a long time for it to be removed from these regions. So it's highly it actually highly goes against the point of ventilation in a clean room. So in the middle, for the second design, the situation is much better compared to the first case. We still have a number of recirculation zones, but the velocity distribution is obviously improved. So we have higher velocities in those regions. Still, the contamination could get trapped, but it takes a shorter time for it to be removed from the domain. And now moving to the third case, you can see virtually no recirculation zones are present. Everything, so most of this plane contains high velocity within, what the high means within the meaning of high for this domain. That very efficiently remove the particles from the interior of the room. So again, here this is a very strong indication of the advantage of this third case over the first and second case. And now let's have a look at the contamination and control. So in this case, we look at the contours of scalar transport that these are essentially those particles that left the contamination source. So on left in our base design, you will see the contamination is completely spread on that corner of the room and has entered those recirculation zones that we saw in the previous slide. Let me just go back for a second. So you will see, so as I said, in the left you will see many recirculation areas on left, and here you'll see where we end up. We have the spread of contaminant on the corner of the room, and the reason that is spread are those, are the velocity patterns that we saw in the previous slide. And in the middle we have a second case. It looks much better. It looks really improved compared to the third case. You see it's completely localized. Firstly, it didn't start to spread. It started to move towards the outlet and leave the room. So it's a great improvement. And as you remember, the difference between these two cases is simply the distribution and number of inlets. So this is great. The problem here is that if you place the source of the contamination in a different part of the room, we cannot guarantee having the same results. So in this case, we were somehow close to the outlets. So the particles that were introduced to the room kind of got removed from the room very quickly. But for example, if you have it in the middle of the room or somewhere that was somehow symmetric in terms of the outlets, we might also still see some spread of the contaminant. So with this, let's move to the third design. Again, the quality is also very good. We see completely the contaminant is localized. It did not start to spread around the room. But the good thing about this design is that wherever you place now the source of contamination, the results are virtually the same. You could expect if you put it in the middle of the room, move it around, if the source is not something that is fixed, is something that moves inside the room, it's not going to change the results. And at the same time, it means that when you're designing the room, you do not have to necessarily design the interior of it at that time. There might be changes in the design, changes in the facilities that are used inside the room. So such a design already, even though it was more work to design, it already introduces some improvements for the future use of the room as well. Okay, so I hope this result kind of summarized why those flow patterns that we looked at were very important. Okay, so now let's have a look at the assignment that we have. So we've prepared a similar case. We have a ventilation in a clean room for you. This case is quite similar. So what you have to do is to simulate a room that has the exhaust in the ceiling. So completely opposite what we had in the cases that I just presented to you. So we have a ceiling exhaust layout. We are still going to do a steady state passive scalar transport analysis, and the CAD model is of course provided for you. We also have like the last time, previous times, we've prepared a step-by-step tutorial for you to carry on this task. So let me just show how we can get it. So if you come to our website and go to forum, you will find you will find the list of categories here, and if you scroll down, you should find the webinar. So you see SimScale webinars here. In here, you should be able to find air conditioning and ventilation webinar. And the fourth session, you see this is the new one. Let me just have a quick look. Is the case that is the homework case that I just explained. So again, a very nice step-by-step tutorial prepared. Also, the CAD model is provided inside the project. So what you need to do is to just import the project, follow these step-by-step tutorial, and you're going to be able to produce the same kind of results as you see as the ones provided in this tutorial. Okay. So with that, we come to the end of today's webinar. I hope you liked it. I think it was very interesting to look at the different patterns of the flow as a result of the changes that we made to the CAD model. And I encourage you to really explore all different types of the parameters that we provide. So not just the CAD model, you can even play around with the simulation parameters. See what happens if you increase the inlet mass flow, if you decrease it, if you do not inject them straight into the domain, maybe inject them with an angle. What happens if you use the turbulence model? So all of these actually could be explored. It's very easy. Essentially the same thing as we went through. You just have to play around with a few numbers, and you can get your results and start investigating them. Okay. So I hope you find it useful. Now, as we are at the end of the session, I would like to go through the questions, see if any of you have questions. So just go ahead and enter them into this questions section in the GoToWebinar app, and I will go over them to answer. Okay, so we have one question. Would it be better to, if the same tiles would be on the ceiling as the one we have on the floor? I would say it could be. It's completely imaginable that placing a uniform removal of the particles from the domain could be helpful. So I think this time for the inlet it worked out. It seems like a good choice, but the best way would be to try it out. So potentially yes. Okay, we have a question: how to make the same good-looking velocity slices at the post-processor? Can I do it in SimScale, or do I have to post-process locally? You actually can produce almost the same results with our platform. So as you know, we kind of recently, it's not that very recent anymore, added many features to our post-processor. At the same time, now we have we have changed the backend of our post-processor, so you can use you can do the rendering on the cloud. So you can't make them look as nice. I'm not, honestly, because others were also involved in preparing these slides, particularly the results that we had a look at. Maybe we could discuss this in the the forum, but you should be able to produce something as good as what we just discussed. So we have a question, are you planning to continue the air conditioning webinars? So far we planned for these 4 sessions with this theme, but we're not going to leave the application, the air conditioning in general, the HVAC area here. We are going to be very active in this area, both in terms of adding new content. Also, if enough of our users are interested in having more series like these webinars or workshops. So I hope, I mean, if there's anything, please communicate this to us in the forum or anywhere else that you see fit, and we certainly consider them in planning our future webinars. Okay, I have a question about the turbulence model. The question is, did the use of, will the use of turbulence model really make a big difference or not? So I go over this very quickly. In case the design of the room is those turbulent clean rooms, it certainly will. So as I said, there are cases where the inlet does not come as a straight set of streamlines, but a flow that rotates, a flow that is turbulent by its nature. In those cases, of course, it makes a big difference to use laminar or turbulent models. In this case, it did not, because the kind of design, the layout of the room, the involved velocities, all of them pointed that such an assumption is completely valid. I have another question. Is there a case configuration where scalar transport simulation incorporates gravity force? If you want to consider gravity when you have particles, it's not going to be scalar transport anymore. The basic assumption behind using scalar transport is that particles move with the flow. They're completely going where the flow goes. So since we're using an incompressible flow for the case of scalar transport, it means that if gravity is important for the case of the flow, then it's going to automatically affect the particles. However, since we are talking about a single domain, we are talking about no change in density, no buoyancy, no multiphase, nothing like that. The gravity in these flows for an incompressible case is not important. And of course, same applies to scalar transport. However, if you're interested in a slightly more complex but realistic kind of analysis in terms of particles that are larger, then you have to use the discrete phase model. There, of course, you can use gravity. You can completely define the characteristics of your particles, their size distribution, and it also would be interesting to do that kind of simulation. Would you have any of the 3 designs in this step-by-step tutorial, or we're just going to check or review when we're going to download the assignment? So the step-by-step tutorial that I showed is similar but not identical to the cases that we just reviewed. So the cases that we just reviewed are going to be available for everyone, but their setup is kind of similar. So I would say if you do this step-by-step tutorial for the assignment, you're completely going to be capable of reproducing the setups of the 3 designs that we just went over in the course of the webinar. Okay, I think these were all the questions that I had, all of the ones that are relevant to the topic of this course, of this webinar. Okay, so with this, I would like to conclude today's session. I would like to thank everybody for attending, also for the nice questions. I encourage you to go ahead and import the project for the assignment. Do how the step-by-step tutorial is instructed, but also go 1 step, 10 steps further than that, play around with any of the parameters and see how it affects the results of the simulation. Okay, so that would be it. Thanks again, and goodbye.